All right. Hi there. Welcome, everybody. Welcome to the Summers Physics 10 students and anybody else who might be watching this. I wanted to take a few minutes here to talk to you about a really fascinating experiment that was done by a guy who's one of my favorite scientists. And the reason I laughed when I said that is I know whoever I'm talking about at the moment is always one of my favorite scientists. But Cavendish was a remarkable person, even among remarkable people. He was a British scientist who was worked throughout like the second half of the 1700s. I think he was born like in 1730, which would have been about 90 years after Isaac Newton. So by this time, he's a generation or so after Émilie du Châtelet and Voltaire, who we've been talking about, and they in turn were a generation or two after Isaac Newton. So by this point, the physics world had gotten used to thinking in terms of Newtonian physics. The Newtonian revolution was well underway. Du Châtelet had added the interesting concept of energy to that, and physics was off and running. I think I've also mentioned before, though, this was right around the moment when chemistry was just getting its start as an empirical science. We often say that if we had to name a single person, which is silly, who did for chemistry what Newton had done for physics, it would probably be the French chemist Antoine Lavoisier. But Cavendish was up there, and he was active in every branch of physical science. He was an absolutely groundbreaking chemist at a moment when there was a lot of new ground that needed to be broken in chemistry. He did fantastic physics experiments. He was an inventor. He was a geologist. He created a number of new scientific instruments that you could use in your research in almost every field. So he left a gigantic mark on the history of science. He would have left an even bigger mark. We might call him the greatest scientist of that age if he had actually told everybody everything that he discovered. As it turns out, we wouldn't know until about 50 years after Cavendish's death some of the things he discovered. It was another British physicist, James Maxwell. And James Maxwell's a giant in the field of electromagnetism, so we'll be talking about him later. But James Maxwell got permission from Cavendish's family finally to go back through Cavendish's old lab journals and read what Cavendish had been up to during his active research career. And shit, there's stuff in there that would not be rediscovered until another 20 or 30 years later. So if Cavendish had actually told us everything that he discovered, that would have set chemistry forward by decades. It would have set physics, especially the study of electricity and magnetism, which, as we will see next week, was really getting underway big time around this same time, the second half of the 1700s. Some of the things that Cavendish learned about electricity, again, would not be rediscovered until the 1800s. Cavendish knew about them. He never told anybody. Now, we've had a couple other scientists also. Now, even the things that he did actually reveal that he had discovered were already enough to rock the world. He changed chemistry to get forever. He changed physics forever. But no, the changes would have been even more profound if we had known about it. I've talked before about a couple of scientists who did have this habit of waiting a long time before they put their results in print. We said Copernicus delayed publishing his most important book until he was almost on his deathbed. We've said that Isaac Newton delayed publishing the Principia for 20 years because he wanted to invent calculus first to back up his physics insights. And they each kind of had a different reason. In Copernicus's case, he delayed kind of through an excess of humility. He felt like he had not cracked some of the crucial puzzles that went along with the heliocentric model of the solar system, with the Earth orbiting the sun. And he was certain that if you just gave him a little more time, he could crack those puzzles. So he just wasn't ready to publish his book yet. And again, it would be later generations, Galileo, who would start to make progress toward cracking those puzzles. In the case of Isaac Newton, it was almost the opposite trouble from Copernicus. Rather than too much humility, Newton had too much ego. He also wanted to delay until he had crucial mathematical results figured out that he could use to back up his physics. But in his case, it wasn't because he was worried that he was misunderstanding or he was worried that he was wrong. He just wanted to be able to shove his enemies' faces in the truth when he published his results. So Newton just was absolutely confident he was right, but he wanted to be able to show beyond a doubt that he was right. Where does Cavendish lie on this spectrum? Well, Cavendish actually had a completely different reason why he didn't publish his results. Cavendish suffered from severe social anxiety. The science of psychology didn't exist yet, so there were not words for for speaking about Cavendish's mental state at the time. But today we'd say definitely neurodivergent in probably multiple ways, almost certainly on the autistic spectrum, and he had several phobias which tended to strongly limit what he could bring himself to do. He had agoraphobia. He was very uncomfortable in wide open spaces, preferred to be indoors in a familiar environment. But he had a absolutely devastating sometimes social anxiety. It's not that he didn't like to talk to people. His one social outlet was he would attend meetings of the Royal Society. Now, the Royal Society sounds like I'm talking about a snooty bunch of aristocrats or something like that. But no, that's the name given to the British Academy of Sciences. So it's the equivalent of the Académie des Sciences that you heard Voltaire and Emily du Châtelet discussing on the Nova video we had. It's England's biggest scientific community, maybe kind of paralleled part of the role of the National Science Foundation in the modern United States. Yeah, he'd attend meetings of the Royal Society, which means meetings attended by people he had known all his life, all the greatest scientists of the day, and he wanted to go to the meeting, they would say, but you'd see him hovering outside the building because he wants to go in and listen to the conversation, and he's also absolutely terrified and overwhelmed at the thought of going in and listening to the conversation. Once he was inside the meeting, if he didn't, on that particular night, turn around and flee back to his own home, once he was inside, the other scientists definitely wanted to talk to him. They knew that Cavendish was one of the most brilliant ones among them, and his insight into whatever puzzle you were stuck on was always immensely valuable. But they also knew that you can't just walk up to Henry Cavendish and say, "Hey, Henry, I've got a puzzle I've been wondering about." You'll freak him out. I mean, again, kind of people with social anxiety can probably relate to this. It's not that he didn't want to talk to them, but it's that he found it exhausting. It would drain his resources. It would throw him into panic mode, and he might, find himself too exhausted to work for weeks after a simple conversation with an old friend who he's known his whole life. So his friends at the Royal Society realized, okay, you can't just walk up and ask him a science question, or you'll just end up throwing him into a panic. You won't get your answer, and you'll be ruining Cavendish's evening. So instead, they found the art of what you do is you walk up, stand maybe several meters away from the chair where Cavendish is hiding. You turn your back so he knows you're not talking to him, and you just idly start musing over the question as if you're talking to yourself. And they said, even if you do this, even if you raise this question in the most non-threatening way, 9 times out of 10, you'll hear one of his colleagues described it as a peeved squeak, I think, from the direction of Cavendish. And when you turn around again, you'll find he's vanished to some other corner of the room, that he can't handle the situation. But the 10th time, you'll be standing here talking into the air about the problem that's bothering you. And behind you, you'll hear Cavendish's voice also talking to the air. He's not answering your questions. In fact, you don't want to phrase it as a question, or he'll realize he's having a conversation and it'll all go to hell. So, but you'll raise an interesting point, and Cavendish will be talking, and a couple of minute or so after you've raised your point, he'll raise a counterpoint, and you'll wait a minute so he knows you're not responding directly to him, but you'll then address that point. And if you do this artfully enough, you can have one of the most productive conversations of your scientific career with Henry Cavendish. But you got to know how to pull it off. Now, when Cavendish himself had a new result to present, I mean, you can imagine it would have been absolutely terrifying for him to say, "Well, I'll just schedule to present my paper in front of a meeting of the Royal Society, and I'll tell everybody about it." Even if he's not going to present his paper to his colleagues in person, just writing up a paper probably to Cavendish felt very much like there's an unseen audience out there who's reading what I'm writing. And again, he found it exhausting and terrifying. And it's not that he never wrote papers, but at any given moment, Cavendish would usually have maybe one or two scientific questions that were his fixation of the moment, his obsession of the moment. And if he discovered the answer to one of those questions, then he would push through the discomfort and exhaustion, and he would write it up, and he would tell the world about it. If he discovered the answer to another question that was not on his very short list of ones that were at the center of his attention at the moment, he would probably say, well, someday I should probably tell people about that. And the notes would go into his journals, and again, for decade after decade, he never would get around to telling people about that. And eventually it would be rediscovered by somebody else. But one of the experiments that he did actually write up and share with the world is an experiment that he carried out actually pretty close to the end of his career. He was active in chemistry and physics and geology and every other branch of physical science, probably from about the 1750s all the way up through the early years of the 1800s. I think he died around 1810. This would be an experiment he published in 1795, so almost the close of the 1700s. The theme of the experiment, well, the way we remember it, is he was filling in actually a missing piece in Isaac Newton's treatment of the force of gravity. I've told you before that Isaac Newton's way of thinking about gravity is that any two objects with mass, this coffee cup and this pen, are always exerting a force on each other. Each one's always being pulled toward the other one. How strong is the force? It depends on how much mass each of the objects has. Make either one 3 times more massive, you'll get 3 times more force. It depends on the distance. If I move them 3 times farther apart, the force goes down. And again, as we mentioned in class, it doesn't just go down by a factor of 3, it goes down by a factor of 9 because it seems to go as 1 over the distance squared rather than just the distance. Now, we would say then to actually turn these units, what units have I got if I've done this? I've got kilograms times kilograms over square meters. That's not a unit of force. To turn this into newtons, a proper unit of force, and to get the amount of force calibrated right, I've got to multiply in this universal gravitational constant. And the fact that this number capital G, which is again a built-in constant of the universe as far as we can tell, it's the same everywhere in the universe, it's the same at every moment in time. It's very different from that lowercase g, which is just the gravitational field at a certain place, like near the surface of the Earth, that's 10 meters per second squared. This is a built-in constant of the universe. It's a really tiny number. That's why I don't notice this pen being pulled toward the coffee cup. I do notice the pen being pulled toward the Earth because the Earth has enough mass to make up for this tiny number g. Well, at Cavendish's time, nobody had yet been able to measure that number g. They didn't even really think of the equation this way. They thought it in terms of proportions. They'd say if you already know the force of gravity on one object, then if you start changing these variables, you can tell how the force will change. But you gotta have a pre-measured force. Now, you could very well ask, how the hell did they not know capital G? I mean, again, Physics 10, we don't delve deeply into the mathematics of a lot of the conversations we have, but you probably remember from an algebra class somewhere along the way, if I've got an equation like this, if I've got one equation, then if there's one variable in there that I don't know, I can always solve for that variable. So why don't I just solve this equation for capital G? Don't I, can't I measure all these other things? Well, let me think about this dumbbell being pulled toward the Earth. I can measure how much force the Earth is pulling on that dumbbell with, no problem. Put it on a scale. I can measure the mass of the dumbbell, no problem. I know the distance from the dumbbell to the center of the Earth. And again, remember, at least if one of the masses is a perfect sphere, you can measure this distance from the center of the sphere out to the other mass. That's one of the things that Newton was able to prove in his 20 years of developing calculus before he published the Principia. So the distance I would want to measure for the Earth pulling on this dumbbell would be the distance from the center of the Earth to the dumbbell. But I know that distance. We've known the size of the Earth ever since Eratosthenes. So you'd say, okay, why can't I solve for g? Because I don't know this. I don't know the mass of the Earth. I can take a rough guess. I know its volume, and I figure it's made out of rock, so I can multiply by the typical density of rock. But it's made out of what kind of rock? I really don't know beneath the first few surface layers that I can scratch. So we didn't know the mass of the Earth. We didn't know capital G. You can say this lets me, and again, they didn't really think in terms of capital G at the time, but in modern way of thinking about this, I could say, I know that capital G times the mass of the Earth is such and such a value, because I could just take the force on this dumbbell times the distance squared, divide by the mass of the dumbbell. I can get G times the mass of the Earth, but I don't know mass of the Earth. I don't know G itself. Well, you could say, but there's other data that Newton was drawing on to develop his law of gravity. For example, he famously figured out the law by thinking about the orbits of the planets around the sun, among many other things, and the orbit of the moon around the Earth. So couldn't I take, say, the planet Venus orbiting the sun, take some data from that orbit and figure out what capital G is? Well, I could look again. I could say, well, now this, the force pulling Venus toward the sun would be capital G times the mass of Venus times the mass of the sun, divided by, again, the distance from the center of the sun to the center of the planet Venus. I do know that distance. I know Kepler had charted out the orbit of Venus very artfully. And by the time of Cavendish, they had also corrected that embarrassing leftover mistake from Aristarchus. They now knew the distance to the sun properly instead of Aristarchus's incorrect measurement. So yeah, we knew this distance. Do I know the mass of Venus? Well, no, I don't. Actually, I can kind of finesse my way out of that, because by studying the orbit, you get the acceleration of Venus toward the sun. And hey, remember from Newton's second law, acceleration is force over mass. So this would be the force of the sun pulling on Venus over the mass of Venus. Hey, that would cancel the mass of Venus out of this force consideration. So I'm off the hook. I don't need to know the mass of Venus. But I'm still in trouble. I don't know the mass of the sun, and I don't know capital G. I do know the acceleration of Venus, which I can, again, force over mass would give me acceleration. So but I'm still left with two things I don't know. So I'd say, well, okay, shit, G times the mass of the sun is such and such another big number. By the way, this does let you know how massive the Earth is compared to the sun. From this calculation, from Newton's law of gravity, you could show that the sun has to be right around 330,000 times more massive than the Earth. So you can fit about a third, it would take about a third of a million Earths to make up the mass of the sun, or a million Earths would make up the mass of 3 suns. So, so that part you could get from Newton's laws, but you still didn't know what capital G was. Now, you could say, okay, well, let's not talk about things like planets and stars where we don't know the mass. Let me just take this coffee cup and this dumbbell and measure the force of them pulling toward each other. Now I've got a different problem. Yes, I can very easily erase all my check marks and question marks and say, can't I just measure the force of this coffee cup being pulled toward this dumbbell? Not the coffee cup being pulled toward the Earth, that's easy to measure. Not the dumbbell being pulled toward the Earth, that's easy to measure. But the force of them being pulled toward each other, can't I measure that? Well, let's see. I know the mass of the coffee cup, that's good news. I know the mass of the dumbbell, that's good news. I know the distance between them because I'm the one who's holding them here. I can measure the distance. So it looks like we're off and running. I don't know capital G, but that's the whole point. I'm trying to find capital G. Do I know the force? Well, up until this point, the answer was always no. I trust that there is a gravitational force pulling these toward each other. If Newton was right about gravity, it seems like the gravitational force should pull anything with mass toward anything else with mass. And as far as they could tell, Newton did seem to be right about gravity. But the force is too tiny to measure. Again, we'd say today because G is such a tiny number. But again, they didn't have this number yet, but they knew that for everyday sized objects like this, the force is far too tiny to easily measure, at least with an ordinary scale or something like that. This is, now, if you could measure that force, then, I don't know what that, I think I dropped the dumbbell on the side. If you could measure that force, then you could measure capital G. And if you could measure capital G, then as a secret bonus gift, now you would know the mass of the Earth, because all along we've known G times the mass of the Earth. Now you would know the mass of the Sun. You would know the mass of Jupiter, because you can analyze the orbits of the moons of Jupiter. If the moons of Mars had been discovered, I'm not sure if they had yet been at this point, then you could learn the mass of Mars. So you can get lots of automatic bonus astronomical knowledge if you could measure the force between these two objects. It's cool. It shows everything's connected to everything else when you say, in an experiment that has nothing to do with astronomy, all I'm doing is measuring the pull of two humble objects toward each other in my lab, somehow that lets me answer all these astronomical questions. I now know the mass of the Sun. I now know the mass of Jupiter. I now know the mass of Mars. That's kind of cool. This is, again, why one of the great things about Newton's laws is they made the universe so much nerdier. Everything was connected to everything else. But how do I actually measure that tiny force pulling toward each other? This is the challenge that Cavendish set for himself. Now, Cavendish, interestingly, was one of the wealthiest men in England at this point. Most of the scientists we've talked about usually end up coming from fairly humble backgrounds, as Ernest Rutherford would one day say about his own childhood. Well, we had no money, so we had to learn to think. But Cavendish actually did have money. His parents were kind of from two very wealthy families. They had united, combined their fortunes. I think Cavendish was their only surviving child, so he had inherited both of their vast fortunes. You wouldn't know he was all that wealthy from his lifestyle. Apparently, he was living on this ancestral estate that he had inherited. Most of it was closed off. The rooms were shuttered up and nobody ever went there, no furniture in them. He didn't devote any of his fortune to personal comfort. What he did apparently devote it to was he had several very well-appointed scientific labs for several different branches of science, physics, chemistry. He had an astronomical observatory in the roof of the place. He had one of the best libraries you could ever imagine anywhere. I'm envious of his library, but for the most part, he didn't live a lavish lifestyle, host grand parties or anything, as you would guess from the fact that he would find the thought terrifying. But he did have the resources to fund any experiment that he wanted to do. Now, this particular experiment, as it turns out, didn't take so much a great budget, as it just took a lot of ingenuity. What Cavendish did is he went out to I think he called it a garden shed, but it was probably as big as a decent-sized house. But he went out to this abandoned garden shed outside his estate, and he set up the following experiment. So if this is a map of the garden shed, Cavendish took two lead spheres, probably about the size of my fist. I think they said they're like 2-inch diameter. Now, lead's a dense metal, so 2-inch diameter is still a pretty heavy object. But he took two lead spheres and he suspended them. Well, in one version of the experiment, he suspended them from a crossbeam that was hanging from a piece of piano wire to the ceiling. So if this map is an overhead view of Cavendish's garden shed, what would a piece of piano wire look like if it's hanging from the ceiling from an overhead view? Well, it would just be a dot. So there's our piece of piano wire. From the piece of piano wire, he hung a crossbar. On the two ends of the crossbar, he put his two lead spheres, equal mass, so they would balance. So it's actually looking a lot like a cartoon dumbbell, or it's not looking all that different from this one. Just crossbar, lead sphere on each end, hanging from a piece of piano wire so that it can rotate freely like this. His plan was he would place another lead sphere. So this pair on the crossbar, they can rotate freely like this. You know, you could spin that dumbbell around that axis of the piece of piano wire. He would then place another sphere that was fixed in place, that was stationary. So he would just kind of build a little pedestal here, fixed to the ground, place another lead sphere on the pedestal. And his thought was this. I mean, obviously each of these lead spheres is being pulled toward the center of the Earth. We know that. That's easy to measure. But he said this lead sphere should be pulled toward the stationary one. Now, I guess meanwhile, the stationary one's being pulled back. That's Newton's third law right there. But the stationary one can't accelerate. Its pedestal is fixed in place. This one can accelerate. So Cavendish's thought was gradually over time, this pivotable assembly here is going to start to rotate this way. And because this sphere is accelerating, it's going to start to rotate faster and faster in that direction. So how is he, it's going to be a ridiculously slow rotation or a slow acceleration. It'll pick up tiny amounts of velocity probably over the course of several hours. How is he going to be able to measure that? Well, he can't stand here next to it and just watch it carefully. Why not? Well, number one, the rotation is going to be so subtle that he probably still wouldn't manage to see anything just looking at it with his unaided eye. But number two, he's another object with mass. So if he's standing near the experiment, then his gravitational pull is going to pull the spheres toward him. I suppose if he stood sufficiently still, you could just say he's taking the place of this other lead sphere. But this is such a precise experiment. If he moves around at all, if his breathing is creating air currents that bother the spheres, that's going to be enough to mess up the whole thing. So no, he can't be standing here looking at the sphere from up close. What he did was he set up a lantern on this side of the room. Now today we would use a laser beam. He didn't have laser beams, so he took a lantern, like a Coleman lantern almost, he covered it with a metal shield so the light couldn't get out. Well, I say then it's pointless. So he cut a little slit in the metal shield so that it sent out a very narrow beam of light toward his experiment. Then on the center of that metal pole, he placed a tiny little mirror. Now, the beam's probably not narrow enough to just hit one point. It's probably illuminating this whole thing, but the mirror is tiny. So the only light that bounces off the mirror is the light that hit the center of that thing. And it makes a fairly tiny little smudge of light on this wall over here. Now, like I said, what Cavendish called an abandoned garden shed was actually a pretty big building by other standards. So this wall's far enough away. This gives you what they call an optical lever. Even a really tiny, almost imperceptible change in the angle of this hanging crossbeam is going to cause this smudge on the wall to move a measurable amount. Now, does he want to be standing over here by the wall measuring it move? Well, no, both because his own gravitational pull could still be messing up the experiment. The air currents he creates as he moves around in the room could be messing up the experiment. So instead what he did was he had a small hole in this wall. He was standing outside in a little kind of annex to the shed with a telescope. He said he had that observatory up into the top floor of his house, so he had access to plenty of telescopes. So he's standing here with his telescope. So he will come out here, he'll set up the experiment, he'll put this thing in place. This will be as close to equilibrium as he can get it. He will then retreat over here so his air currents and gravitational fields are no longer messing anything up. And over the course of hours, he'll be watching the smudge of light over here as it gradually begins to move across the wall. And it will. The attraction that this sphere exerts on this one. So first he'd let the whole thing come to equilibrium probably. Then he'd put this sphere in place, and as the equilibrium is disturbed and as the crossbeam rotates this way, that would cause this smudge to move across the wall a tiny amount, maybe a millimeter in the first hour. But then because of the way acceleration builds up, maybe 4 millimeters in the next hour, maybe 9 millimeters in the next hour. He would have already kind of carved little gradations over here so that in his telescope, he's got a length scale to measure how far that thing moves. But By measuring how quickly that smudge of light accelerates across the wall, you can measure how quickly this crossbeam's accelerating into motion. And because the thing that's making it accelerate is that very tiny gravitational force right there, you can just take Newton's laws of motion, work backwards, and you can deduce this gravitational force. And Cavendish did. So again, what does that allow him to do in the context that we would say today of Newton's universal law of gravity? I'm going to erase my check marks, erase my question marks, and I'm going to ask again in this equation that Newton had for the force of gravity between two objects. For this particular experiment, which things do we know, which things do we not know? Well, we know mass number 1 and mass number 2, because this time, again, neither one means the mass of the Earth. Mass number 1 and mass number 2 are the mass of this lead ball and this lead ball. And they're both things that, he provided for the experiment. He knows their mass. We know the distance between the two masses. Again, it would be from the center of this one to the center of this one, and he can just physically measure that in his lab. And for the first time, we know the force that those two masses exerted on each other. Well, for the first time for masses that small, we know the force that the two masses exerted on each other. This is, what Cavendish had just gone to great pains to measure. So if I know everything except for capital G, I can now solve for capital G. Now, if you took the data from Cavendish's experiment, it would lead to a number that was right around what we say today, somewhere around 6 or 7 times 10 to the negative 11th in modern metric units. By the way, the metric system was just being invented in France around the time that Cavendish was doing this experiment. So he probably wasn't using metric units yet. He was using old imperial units and sliming his way through, despite the fact that they didn't have a real working unit of mass yet in the imperial system. But he was making do with imperial units. But if you asked, if you read the paper he published, did he publish a paper saying, I finally measured that constant capital G? Well, no, they weren't really thinking in terms of capital G. And actually, to Cavendish, he didn't really think this experiment was about Newton's law of gravity. He thought the experiment was about, well, I guess I erased what I had up there before, which was, remember, just from looking at the fall of an object in free fall near the Earth, you can't deduce capital G, but you can deduce capital G times the mass of the Earth. So this had long been known. Again, they wouldn't have put it in that language, but they had long had the data that would have let you do this. Now that Cavendish had told you what capital G was, you could deduce the mass of the Earth. That was actually the obsession that Cavendish was after at this moment. He wasn't trying to measure capital G. He wasn't trying to go back and improve our understanding of Newton's laws of gravity. If that was all he had accomplished in the experiment, it might have gone down as one more experiment that he left notes of in his lab journals and that Maxwell discovered 60 years later or something like that. However, Cavendish at this moment was not, like I said, he was active in many branches of science. Which hat was he wearing right now? Was he wearing his physicist hat? No, he was wearing his geologist hat. He wanted to know the density of the Earth. Remember what I mentioned to you, that the only reason we don't know the mass of the Earth is just, the reason we can't calculate the mass of the Earth from its volume is because we would start out not knowing what, types of rock the different layers of the Earth are made out of and all that. This is what Cavendish wanted to know. He wanted to know the average density of the Earth because he thought it was one of the most pressing questions of geology at the time. And this was the question that he was sufficiently obsessed with that, if he had to, he would even kind of face his own demons and put pen to paper and tell the world about these results. So, Cavendish's paper was titled something about the density of the Earth. If you kind of asked Cavendish or his close colleagues at first, what did you accomplish with this experiment? He would say, I weighed the Earth. In fact, they said that later generations of Cavendish's family would take people on tours to see this building where the experiment was done, and they would probably say, this is the building where great-great Uncle Henry weighed the Earth. So, to Cavendish, what he had done was, by a roundabout method, he had told you the mass of the Earth. And since we already knew the volume of the Earth, he had figured out the density of the Earth. So a strong clue toward what the Earth might be made out of deep inside. But from our point of view as physicists looking back, we would say what Cavendish did was he allowed us to finally write Newton's law of gravity in the familiar form we write it today, and finally put a number to this value, capital G. And also, interestingly, like I said, he had added a bunch of data to astronomy. We now knew the mass of the sun from watching the other planets orbit around the sun and knowing capital G to finish that calculation. We now knew the mass of Jupiter from the orbits of Jupiter's moons that were, again, driven by this universal force of gravity. I forget when the moons of Mars were discovered. I forget when Saturn's rings were examined closely enough that we could actually tell how quickly the particles that make up the ring are orbiting Saturn. But any object which is being orbited by another object bound by gravity, you now knew the mass of the central object. So yeah, a lot of consequences on one experiment, but I love the ingenuity of this thing. I find this an intensely difficult experiment to pull off even today when we are armed with lasers instead of this old-fashioned hooded lantern and a little bit of mirror over there. I still can't get this one to work right. I know a lot of people who are less of a klutz than I am, and they can get it to work right, but it's a difficult experiment, even by today's standards. To pull it off in 1795 just fricking blows me away. And the fact that it's one of the small number of experiments that Cavendish himself found important enough that he could actually, again, bring himself to communicate it to the world is awesome. All right. I think that's about it for now. I will talk to you all soon. Take care. If I can figure out how to turn this thing off.